Hello friends, today we are going to learn that the Einstein's postulate of quantization of energy and the photoelectric equation. We know that Max Planck, he used the idea that quantization of energy to explain the black body radiations. In 1905, Einstein modified the model of Max Planck, which is used to explain the black body radiation, such that he assumed that light behaves as a particle and it liberate or it release energy or absorb energy in the form of quanta, or we can say that this quantum of energy is known as a photons. That means the quantum of energy, it is a photon, and this was assumed by Einstein. Also, he assumed that the energy of this photon, which is nothing but E is equal to h nu, where h is Planck's constant and nu is the frequency. And this h, Planck's constant, which have value h is equal to 6.63 into 10 to the power minus 34 joule second. This is the constant which is known as an Planck's constant. This relation is equal to h nu, which is known as an Einstein's relation, where this E have significance energy, h is Planck's constant and nu is the frequency. The particle nature of these radiations, we know that this energy term which shows the particle nature of this photon, and this frequency term which shows that the wave nature of this photon. That means this energy which is directly proportional to frequency, because h is the Planck's constant which is constant, and this we can say that inversely proportional to wavelength, that means 1 upon lambda of this incident radiations, because E is equal to, we know that h nu, which is equal to h c upon lambda, where nu is equal to c by lambda, and c have the significance of velocity of light. So we know that for maximum frequency the energy of incident radiation is maximum, and for minimum wavelength, or we can say that shortest wavelength, the energy of incident radiation, it should be large. We can find out the energy of photon if you take that, suppose there is a ultraviolet light having a wavelength, suppose lambda UV, which is equal to 3000 angstrom unit. Then we can estimate the energy of photon such that, suppose E is equal to h nu, or this is equal to h c upon lambda, or this is equal to, if we substitute the values of this, Planck's constant have value 6.63 into 10 to the power minus 34 joule second, multiplied by velocity of light 3 into 10 to the power 8 meter per second, divided by lambda UV, or ultraviolet light, which is equal to 3000 multiplied by 10 to the power minus 10 meter. All these values are in SI system. If we calculate this, we know that 3 in 10 to the power 8, this is nothing but 6.63 into 10 to the power minus 19 joule, or this, if we calculate in electron volt, 6.63 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19, or this should be equal to 4.14 electron volt. That means the energy of photon This is in electron volt, 4.14 electron volt. We can measure this photon energy in electron volt.